This photograph captures the sheer physical scale of the global energy transition. We are currently installing enough solar panels to cover entire cities, bringing cheap, abundant power to the grid at a record pace. But this massive infrastructure project has a strict operational limit. The moment the sun dips below the horizon, millions of acres of silicon glass immediately stop producing power. The grid actually struggles to handle these extreme swings in supply. On particularly sunny days, operators are forced into a process called curtailment, literally shutting down perfectly good solar farms simply because they are generating more electricity than the grid can safely absorb at that exact moment. Then, a few hours later, the situation sharply reverses. Everyone comes home, turns on their appliances, and energy demand spikes precisely when solar output hits zero. Power companies have to scramble, buying up expensive electricity from alternative sources just to fill the gap. The central challenge for modern power infrastructure has shifted. Generating clean energy is largely solved. The real problem is figuring out how to move that energy across time, shifting it from the sunny hours of overproduction to the dark hours of peak demand. For decades, engineers have chased a highly ambitious solution to this timing problem: space solar power. The idea is to park massive panels in orbit, far above the weather and the Earth's shadow, where they can harvest uninterrupted sunlight. Recently, a Virginia-based startup named Overview Energy has brought this concept back into the spotlight. They have secured millions in funding and signed a memorandum of understanding with Meta to deliver an initial gigawatt of orbital power. Their engineering pathways sound straightforward on paper. Deploy orbital arrays to capture solar energy, convert that electricity into a laser, beam it through the atmosphere, and turn it back into usable grid power on the ground. But from a physics perspective, this process leaks energy at every single step. Converting sunlight to electricity, forcing that current through laser diodes, beaming it hundreds of miles through atmospheric interference, and converting it again on Earth results in massive, unavoidable power loss. If raw efficiency is the primary goal of electrical engineering, it raises an obvious question. Why are major tech companies and investors pouring millions into a system that is specifically designed to waste so much power? To understand the logic, you have to look at how they position the hardware. This animation maps out their orbital strategy, placing arrays in a high, geosynchronous figure-8 pattern. This allows the satellite to hover over a specific region of the globe, staying bathed in constant sunlight without burning through heavy propellant to maintain a rigid, locked position. While in the sun, the satellite converts its gathered energy into a near-infrared laser beam. Rather than firing a concentrated pinpoint, the array casts a wide, diffuse cone of light back down to the surface. Because the beam is dispersed over a massive geographic footprint, it is completely invisible to the human eye and passively safe. The actual energy density hitting the ground maxes out around 300 to 600 watts per square meter, which is significantly weaker than the direct sunlight you experience on a clear afternoon. But the real ingenuity lies in the specific color of the laser. Overview Energy tuned their near-infrared beam to land between 900 and 1000 nanometers. That exact wavelength perfectly matches the silicon bandgap of standard commercially available solar panels. By beaming down the precise frequency that our existing panels are built to absorb, they bypass the need to spend billions constructing specialized microwave receiving antennas. They can aim the laser at the solar farms we have already built, effectively forcing them to generate power in the middle of the night. Even with that clever optical match, the total round-trip journey from orbit to the local power lines remains physically inefficient. A tremendous amount of absolute energy is lost along the way. The justification for that loss is purely economic. This chart plots typical daytime solar production against consumer energy prices. At noon, supply is high and electricity is cheap. But as the sun sets and solar supply drops to zero, the market price of a megawatt-hour skyrockets. Overview Energy targets this exact window. By catching sunlight in space and beaming it to dormant panels on Earth, the system sells electricity when the grid is most desperate. A single unit of energy sold at night generates 3 to 5 times the revenue of a unit sold at noon. The physics paradox is resolved by market reality. The system is not engineered to be physically flawless, taking cheap, curtailed sunlight and converting it into premium, high-value electricity. This engineering strategy is moving past the whiteboard phase. Overview. Energy has already completed proof-of-concept testing, using airplanes to beam infrared light down to conventional solar panels, validating the core conversion physics that secured their agreement with Meta. The next step is orbital validation. They have booked a rideshare slot on a SpaceX Falcon 9 to deploy a low Earth orbit satellite, testing their ability to actively track and hit ground targets from space. Yet the entire plan faces one towering, unproven obstacle. Moving from a single test satellite to a commercial fleet requires launching hundreds of massive, heavy arrays into high orbit. At current launch prices, the transport fees alone would bankrupt the project. That is why their financial model is tethered to the vehicle in this photograph, SpaceX's Starship. The space solar business case hinges on next-generation heavy-lift rockets radically driving down the cost per kilogram to orbit. Without that impending reduction in launch costs, the economics fail, and the space solar concept remains trapped in a spreadsheet. Even if a fleet of orbital lasers successfully comes online, they will still rely on the towering steel and high-voltage lines shown here. We will always need robust physical grids to distribute power across continents and balance the loads. Securing our renewable future doesn't require tearing down our current world to build futuristic megastructures. Instead, it relies on pragmatic engineering, finding clever ways to hack the infrastructure we already possess, ensuring the grid keeps humming at night.